want to finish off today's, I want to finish off 16.3, the fundamental theorem of line calculus. And
I noticed on the online that, are we going to be doing 16.4 on our test, or?
Yeah, we will.
Okay.
It's coming up. As soon as we finish this one, we'll start 16.4, which is called Green's theorem. After, no surprise, after a mathematician called Green. So this here is just like our last.
Was he green like the Incredible Hulk?
No, it's green as in his last name was Green. Oh, you are in a good mood today, I can tell. Oh, God. What did you do that for? I've now got this vision of the Hulk doing mathematics. This is not a good vision. Getting annoyed that the number's not working and ripping them up. Right, so if I do the Hulk, it's all your fault. Okay, so what I want to do here is basically just do one last question on using basically this trick here. That if you want to find a line integral, what you can do is you can find the potential function and evaluate it at the start and the finish. So this one is similar to question 19. It's a three-dimensional, which I like. Here's our space curve. Actually, in the homework, they tend to do the space curve as x equals t squared, y equals t plus 3, and z equals 2t minus 1. But I just like writing them that way. And they also very often write the vector function, write the vector field up here in terms of this I, this guy ji, plus this guy k. So when you go and look at your homework and you say, but that doesn't really look like 19, that's just the way I write it, because to me that's much more concise and it's easier for my brain to keep track of all these bits and pieces. So how do we approach the question of finding this line integral? It'll either be the integral over the curve C of the gradient of f dot dr, or they will write it as the integral over the curve C of capital F dot dr, or they will just ask you to find the work done. You know that these are exactly the same thing, right? It's not like one of them's a different question than the other two. And in fact, I tend to look at that one because to me that it just works. So what do you do? The first thing, well, one of the things you can do, probably should be the first step, find the coordinates of the starting and finishing points. Well, in this question, you're told it starts there, right? And it finishes here. So if you put in 0, you'll get 0 squared, 0 plus 3, and 0 take away 1. And so your starting point will have that coordinate. And if you want to find where does this thing end, well, it ends when t is 1. And that's going to be 1 squared, 1 plus 3, and 2 lots of 1 take away 1. And so the end point is 1, 4, 1. And what is really cool about the fundamental theorem of line integrals is that we don't care what that curve does. All we care is that it starts here and it finishes there, because they're in fact the only two numbers that matter. So now we find in step 2 our potential function, the little f. And we find it because we know it has this property, that the gradient of f is our vector function. And our gradient is df by dx, df by dy, df by dz, and it's going to equal 2xz plus y squared, 2xy, x squared plus 6z squared. And so we're using this property to find out who little f is. And so what you do is you match the x's, you match the y's, and you match the z's, and you essentially integrate. So if I match the first term, which is this guy, it should equal 2xz plus y squared. And then I integrate it with respect to x. Technically, I guess should call it partial integration. I integrate it. Now, what does that get me? Well, if you integrate this with respect to x, you get x squared z. If you integrate y squared with respect to x, you get y squared x. And you get an arbitrary constant. And the arbitrary constant is anything that doesn't have an x in it. So I'm going to call it g of yz. And we normally write that down as just a placeholder, right? It just allows the math to work out good. Then I go and I do the second one, which is this guy. And it's equal to 2xy. And I do an integration with respect to y. And when you do this guy, you get, what the heck do you get? You get xy squared. Plus an arbitrary constant that doesn't have a y in it. So we'll call it that guy. And then lastly, you do the third one. And he's going to equal x squared plus 6z squared. And you integrate it with respect to z. And x squared becomes x squared z. And this guy here, becomes, can I just check that? I'm just curious. Oops, wrong one. Okay. I get thrown by the 6, but it's there, so trust the math. Add 1 to the power, divide by the new power. Okay. Plus an arbitrary constant that doesn't have a z in it. So I'll call it that. Now I'm going to go step 3 because I need more room. So we're at this point here, right? From these 3 guys, we should be able to find what the potential function f is. Well, it has to have these 2 terms in it, it has to have this term in it, and it has to have these 2 terms in it. And when you put that together, let's see what we get. Would you agree that there should be an x squared z?
Yes.
Would you agree there should be a y squared x, or xy squared, which is probably a better way of saying it?
Yes.
And there should be this guy in it. Are you comfortable about how you combine the 3 into a single equation where everybody gets to be present? Does that make sense how we did that? It's not an adding process, it's a combining process where you make a single function that has all the pieces that are at least in one location.
Or merging.
Merging, yeah. Merging, yeah. I like that. Merging, yeah. So you merge them together to make f. And do you know these little weird G's, H's, and K's? They are what allows this merging to happen. For instance, see if you look at this top one, you've got this guy, you've got this guy, but you don't have 2z cubed. But wait a minute, isn't g of yz 2z cubed? That's the placeholder for where the 2z cubed could live. So it is totally acceptable. And so you then get to step 3, the final step in these questions, which is really get the answer.
Sir, I have a quick question. I have a quick question about that actually. So let's say that when we had the partial derivative of x, the partial derivative of f in respect to x, we get whatever we get, which is the x squared z squared, or the x squared z, and then on the last one, if we had minus x squared z, so how will we handle that case?
If you got a contradiction, you're wrong. So go figure out what you differentiated wrong or what you got, because it doesn't work. So what that would be showing me here is that it's not a conservative field.
Okay.
Remember, there's a restriction on this process. This only works if it is a conservative field. So what you've just discovered is that it wasn't a conservative
wasn't.
field, and so
Okay.
it didn't happen. So you can't really fix that because this technique is not designed to work with it.
Okay.
But that won't happen because the questions are all conservative fields.
Okay. All right.
Right. So we want to find this guy. I'm going to just write down that version. Me personally, I prefer that version. These are exactly the same thing, right? So you find the value of the function at the end, take away the value of the potential function at the start. Now, at the end, it was 141. And at the start, it was 0, 3, -1. And what do I have as an expression? I have all of this. Okay, so it's going to be x, it's going to be y, it's going to be z. So what do I get? I get 1 squared times 1 plus 1 times 4 squared plus 2 times 1 cubed. That's this guy. Take away, well, that's good because that makes that 0 and that 0. And basically, you just have 0, 0, and 2 times -1. So I could actually put it in here. Take away 0, 0, and 2 times -1, which is that. And I get 1, I get 16, I get 2, and I take away -2, so I add 2. And I'm assuming I didn't screw up anywhere. The answer I would get would be 21. So you find the value of the function at 141, and you get the answer 19. Take away the value of the function at the end, which was -2. So take away -2 adds another 2 to the answer, and that's where the 21 came from. Are we cool with the fundamental theorem of line integrals? This basic type of question. It has a lot of structure to it, which many students like, right? There's a do this, then you do this, then you do that. I'll give it a few seconds and then we'll call this one done, unless there's questions. Any problems, any questions? Okay. Then that is the end, for the time being, of the fundamental theorem of calculus. And I think it was Brooke who said, are we doing 16.4? Yes, we are, which is what's going to happen for the rest of the week. And it's called Green's theorem. I don't know an awful lot about the guy Green. I suspect he's English, which is probably why I don't know an awful lot about him. I much prefer Scottish mathematicians, but I'm biased. So he came up with an interesting technique for doing these types of line integrals. We haven't done an awful lot of these line integrals, but we have done some. If you want to do this line integral, he figured out that this single line integral can be turned into a double integral. And C is the original curve, and it's something called positively orientated curve. And D is the region bounded by the curve C. So we are talking about a situation where this curve C has a start and a finish, and it basically loops round. So can you imagine that C is this kind of curve? That's what C looks like. Now, what does positively orientated mean? As you go round, and it's a closed loop, which is another term you'll see being used in other textbooks, and well, actually in this textbook as well, they'll probably use that term. And basically, a closed loop just means the curve starts and finishes at the same point, right? Blah, blah, blah. Positively orientated means if you are an ant and you are walking around the outside of it, the internal shape is always to your left. You can also think of it as being going anti-clockwise round the shape. Are we comfortable then that C is going to be a closed loop? Right. And that positive orientation. Now, what will be the problem when it's going the other way around? Imagine you're going round the curve, but in a clockwise direction. Not a lot. If you go one way and the answer is 42, if you go the other way, the answer is negative 42. So it's not a hard fix. And for the purists amongst us, do you know that Green's theorem is a counterpart to the fundamental theorem of calculus from Calc 2? Might not look like it, but it is actually. In fact, the fundamental theorem of calculus, this guy, comes from here. So it's kind of back to front, but you can prove it by using this. So what does that tell me I'm going to do? It says this line integral is going to turn into a double integral. And sometimes that can be a lot easier to do than the original line integral is. So this is just a trick or a process that allows us to get line integrals that are easier to do when they're converted into this double integral. Okay, so that's really what it's for. There is an interesting fact here. These line integrals, the P and Q guys, they are not conservative fields. Because if they were a conservative field, what would be the answer to every single one of their line integrals?
0.
0. So you may actually get a question, in fact, I'm be darn surprised if you didn't, where your integral ends up being 0, right? In other words, this answer is 0. And if that does happen, it's because they threw in a conservative field question. So Green's theorem is, well, what do you do if you want a line integral and it's not a conservative field, right? Well, we could do it the parametric way, but God, that can be really ugly, if not impossible sometimes. So here's another strategy for doing it. So far, so good? We okay? Last chance, we're going to start looking at applications.
Wait,
I
do have one question. In the double integral, is that like the partial integral of P and Q, or yeah?
This double integral here?
Yeah.
It's a straight d x dy.
Okay.
So it's not a partial, it will be, well, do you know when you do dx dy, I think they blur. Are they really not the same thing now?
You know, I think, yeah, they do blur a bit.
Right, I'm having issues with Windows. Everybody that's talking to me is now in the way of the window I want to open, and I'm frightened to close it in case I close the Zoom meeting. So bear with me as I look intensely at how the heck I'm going to get this to go away. Right, that window's gone. That's good. Now, where's my other window? We got it. Okay, I'm good. I'll just leave yous in the road, and that's fine. So let's just figure out one that we can do. Okay, we'll start off with a very simple question, which is question 1. We're being asked to find the line integral. It's y e to the x dx plus 2 e to the x dy. And C is described as a rectangle using these coordinates. Okay, so let's identify some key features. This fella is called P, and this fella is going to be called Q. It's important we know who's going to be called P and who's going to be called Q, because can you see what happens up here is that the Q gets an X and the P gets a Y, and this goes here and that gets subtracted there. So we kind of have to know where all the bits fit, right? Now, this fella looks something like this. Origin 40, 43, and 03. So if I join these together, can you see that C is a closed loop? And you're going in this direction. And why do I know that? Because you go from the first coordinate to the second, to the third, to the fourth. So this is C, and can you see that the region inside it, that's what they're going to call D. Is this still a positively orientated?
Yes.
Right. Suppose they decided, because they felt like confusing you, suppose they decided to go around this rectangle but the other way. Would that be a big problem?
No.
No. Couldn't we just get the answer the way we were always going to get the answer, but remember to change its sign? So if the answer is 8, we'll make it -8. If the answer is -20, we'll make it +20. So that's all you need to do if it's not going round the shape the way you want it to, right? So if it decides they wanted to go
And
this
we're
way,
pulling, and we'll pull the identity of from 6.3 that it's always counterclockwise, if stated, if unstated, but if it's stated.
if it's unstated, we'll assume yes that it's going counterclockwise.
Okay.
Do you use the word anti-clockwise, or is that a British thing?
Counterclockwise.
So you never use the word anti-clockwise. Is that a weird word then?
We should use it.
Oh, thank you. Why? Just it's easier to say?
It's
Sounds more-
easier to differentiate between the two rather than
it
clockwise
sounds
and
different.
counterclockwise, anti-clockwise.
Okay. So you don't mind if I just keep saying that then? Right. That'll make my life easier, because I'll probably, if I start having to remember which word is which, I just get confused. Okay, so we got the basic building blocks here, right? We know P, we know Q,
That's
we got the region D. So what we need to kind of now do is put the package together. And so this integral here is going to be the double integral over my region D. If you differentiate this guy with respect to X, you get this. And if you differentiate this guy with respect to Y, you get that. dA. Are you comfortable about the two bits that I just got? This guy with respect to X, right? Guess I could put it up here. Take away, did I just do that wrong? I did, right. And this guy with respect to Y. So we are looking at the double integral of e to the x dA. Right, you know, dA is a placeholder. It's probably going to be a placeholder for dx dy. Or now and again, can you imagine there might be situations where polar is just easier, right? In which case it'll be an r dr d theta. And would you agree this guy is a classic dx dy situation? Right, if you want this region D, wouldn't you do a dx dy situation? So it's going to be the integral of e to the x from x equals 0 to x equals 4, and from y equals 0 to y equals 3 of e to the x dx dy. Are you comfortable about this became that?
Actually a little confused about how
Okay.
dq dx became 2e to the x.
Okay. dq, well, this is q.
Okay. Okay.
So you do this guy, that's where it came from.
And then we just
dq by dx, this guy,
oh,
take away dp by dy. If you differentiate this with respect to y, you just get e to the x. We good?
yeah.
Right. So this fella here, oh, actually, isn't this guy here separable? Hey, integrate that guy, you get y from 0 to 3 gets you 3. Integrate this guy, you go what? E to the 4, take away e to the nothing. And there's your answer. It's 3 lots of e to the 4, take away 1. And that wasn't that hard, was it? As a double integral, it was actually quite easy. Are we good? Right, now, if I had to do this the old-fashioned way, this question would have to be split into 4 separate integrals, one for each of the 4 lines. I'd have to parametricize each of the 4 lines and then do 4 separate integrals in terms of each of them. And when I finished, I would get this as my answer. Okay, let's do one with a circle in it. I like circles. Oh, perfect. We are going to find the line integral of the closed loop C of 2y cubed dx minus 2x cubed dy. And C is the circle x squared plus y squared equals 16. So if you want to imagine what C looks like, we'll assume that you go anti-clockwise around the circle. Right, and that's C. So D is the inside. Now in this question, this guy is P, including the negative. This guy is Q. This integral, I guess I should write it down there. This line integral, 2y cubed dx, take away 2x cubed dy, can be written as a double integral over the region D, dq by dx. If you differentiate this guy with respect to x, you get negative 6x squared. Subtract. If you differentiate this guy with respect to y, you get 6y squared dA. So this line integral has the same value as this double integral. Now, there are a couple of really good clues here. Would you agree that when it's a circle, polar worked better with circles and parts of circles? So if I'm going to look at this as a circle question, which I am, wouldn't this region D be polar? And wouldn't it be r between 0 and 4, and theta goes between 0 and 2 pi? I'm going to do a little bit of work on the double integral before I go any further. If you look at negative 6x squared, negative 6y squared, that has to get converted into polar, right? But if I pull out the negative 6, do you see it's going to come out a little bit nicer? What will the x squared plus y squared look like?
R squared.
Right. So what we've got really is negative 6r squared times r dr d theta, and the range of d in polar, because it's a complete circle of radius 4, is simply just going to be r equals 0 to r equals 4, and since it's a full circle, it's theta and 2 pi. Do you see really what's happening here is, aren't we winding back to double integrals that we did weeks ago? In particular, double integrals with polar in this question. So, is this variable separable?
Yes.
Yes.
So I'm going to go a 0 to 2 pi of, who cares, 1. And I'll do a 0 to 4 of negative 6r cubed. Not sure that was the best choice, but too late now. This guy here will get you 2 pi. This guy here is a little bit more work. It's going to be add 1 to the power, divide by the new power, evaluated at 0 and at 4. 4, 16, 256, 125, 256, 256, 128, 328, 384. Take away
Very
384.
good.
Was it right?
Yes.
Good in Emil. Whew, okay.
It is 4 to the 4th is 256. And then you times it by negative 6 over 4, you get negative 384.
You know, I deserve a thumbs up for doing that. I did good. Nothing. Not one thumbs up. Just well done. Okay. This is the answer. I'm making an assumption here, which is fine, and that this answer is negative. But it's okay for line integrals to be negative, so I'm not too worried about that.
Shouldn't they be multiplied though?
So again, oh, right.
There we go.
And it's still negative. We double check that.
Good.
I got a good, and I can verify it is negative. Suppose they decided to go round that circle in a clockwise direction, which is actually considered to be the negative direction. What would be the final answer?
It would be positive.
Yeah. Wouldn't you just remember to change the sign at the end?
Hopefully.
In which case, you keep the working exactly the same. So my question is, suppose instead of going round this circle anti-clockwise, they said you were going to go round this circle in a clockwise direction, right? So, positive orientation is anti-clockwise. You go that way, right? Negative orientation, right? You go clockwise. And you might think that that terminology is back to front. But if you think about it, when you do a unit circle, what is the positive direction as you travel around the unit circle? Isn't it anti-clockwise?
Yes.
Right. Now, maybe there's Martians out there. And Martians, you might not know this because I'm making it up, but Martians have always made their clocks go anti-clockwise. Now, if Martians made their clocks go anti-clockwise, wouldn't we have very little problem about positive and negative orientation? Wouldn't those two things kind of make sense, right? So what are we left with? We are left with the idiosyncrasies that the first people who decided to make clocks made them go that way and not the other way.
Even though they wrote in the other direction, which is weird.
Go figure, right? Go figure, right? So we are at the mercy of historical idiosyncrasies for why in some situations things look back to front. That
Sometimes I wish that they would still teach writing the other way because I'm left-handed.
Oh, yeah, but I wouldn't like that. But yeah, you would. I got you. Right. I'm looking at some horrible question. Yeah, we have time for it, but I want to do that one right now. Okay. This one is like question 5. There are a lot of different versions of how these line integrals get created. So I'm picking one that looks very familiar, although it's going to take me a little bit of time to set it up. It's this guy plus y squared. It's this guy plus x squared. The curve C is an arc. Y equals cosine x. And that arc goes from negative pi upon 2, 0 to pi upon 2, 0. And then it's a line segment. And that line segment goes from pi upon 2 to negative, pi upon 2, 0 to negative pi upon 2, 0. Okay, let's get this thing sorted out because I'm a visual person and there's just too much going on there. So, y equals cosine x. Well, we know what cosine x looks like. Looks like that. Well, actually, looks a lot more like that, right? But we're only going to start here and finish here. So we are traveling that way, agreed? That's what this bit means. And then we're going from here to here, which means we're going back that way. Can you see the curve C now? And can you also see D? Are we comfortable with that piece to the puzzle? So far, so good. Now, who is P and who is Q? Because we're being asked essentially to find this fella. And you recognize this fella as a line integral that calculates your work. This line integral can be written as P dx plus Q dy. And P is him, and Q is him. So essentially, we're being asked to find this line integral. E to the negative x plus y squared dx plus e to the negative y plus x squared dy. Are we comfortable about how this became that? Yes.
Why is it not like the right half of a circle? Why is it a horizontal semicircle?
Oh, because it started at negative pi upon 2, 0, which is here. And the cosine traveled until you got to positive pi upon 2. So it's this piece.
Which means we'll have to flip our answer in the end.
But only the sign of it, agreed? But we just need to find out what the answer is. And if it's 14, the right answer is negative 14. And if it's negative 22, the right answer will be plus 22. So what Brooke's saying is right. This is a negative orientation, isn't it? And when it's negative orientation, we have to accommodate for that by making sure that our answer has its sign switched. So now that I've got all the pieces, I'll call this guy P and I'll call this guy Q. Let's see what the double integral over D would look like. It's this guy. The partial derivative of q with respect to x, the partial derivative of p with respect to y, dA. In this case, it's going to be a double integral. If you differentiate q, which is this guy here, if you differentiate it with respect to x, don't you just get 2x? And if you differentiate this guy with respect to y, you get 2y. So we have this fella. This particular thing, it might look like half a circle, but it's actually a cosine curve. So I'm not going to do any polar on this. I'm going to do a dx dy. Actually, I'm going to do a dy dx if I'm being exactly specific. And the x's are going to go from negative pi upon 2 to positive pi upon 2. And if you imagine, so well, since we've done these guys, do you imagine the little vertical rectangle? Won't that go from a y equals 0? And what will the top limit of the y be?
1.
Cosine x.
It's not x, yeah, it's, I've lost the guy, cosine x, here it is. Here. Are you comfortable about the double integral limits in this question? The x goes from negative pi upon pi, and the y goes from the bottom, which is 0, to the top, which is the curve y equals cosine x. And because of that, the y has to be done before the x is, so it's not variable separable. At this point, yeah, I might as well finish it. At this point here, then it's going to be negative pi upon 2 to pi upon 2. If you integrate this with respect to y, you get 2xy, take away y squared. Evaluated at y equals 0 and y equals cosine x. So you're going to get negative pi upon 2 to pi upon 2. When you plug in a cosine x for y, you get a 2x cosine x, take away a cosine squared x, minus a whole load of zeros. So you're now looking at that integral with respect to x. And I'm actually kind of glad now that I did that. I was going to do a dot, 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 because now that I see it, there's a fair amount of work to do. In fact, there's two different things. So I would probably split them up. Okay, let's get the cobwebs out. Calc 2, you want to integrate 2x cosine x. What technique are you going to use?
Integration by parts.
Correct. Who is going to, if you do the FG version, who's going to be the F and who's going to be the G?
X is your non-differentiated one.
Sounds like you're a UV person.
I'm
So
a
it's
person.
okay. Then you do it UV, and that works perfectly fine. In this case, F would be 2x, and the G would be cosine x. Right? How about cos squared x? That is not going to be an integration by parts. How would you tackle cos squared x?
Just apply the formula.
That's great. Do you have it off the top of your head?
It's going to be 1/2 plus 1/2 of cosine 2x. Oh, 1, yeah. Oh, that, yeah. I usually just distribute the 1/2.
Distribute a half and it makes perfect sense, right? I'd probably pull it out, but who cares? It works. Right, I do all of that and I get the answer 42 and you're dead happy and you move on and you stick it in WebAssign and it says you're wrong. By the way, the answer's not 42, but just pretend it was, right?
You gotta flip your sign.
Right, because we're going clockwise now.
Yes, we're going clockwise, or we're going negative orientation, which is what they call it, right? And do you see how a little hiccup like that can frustrate the heck out of you? Because you could be doing a really, really intricate question and you did it exactly right. And the only thing was wrong is you forgot the orientation issue.